cross products. Although I sent out an email, let me announce this again. Tomorrow we'll have the quiz, and there will be 3 questions, all from the 6 videos I sent. And so questions will be very similar to those, so make sure that you practice those. On Brightspace, I have a PDF file of similar questions and answers, so you should try those questions and see if your answer agrees with what I put there. Okay. Right. So let's talk about cross products. And there's always physics motivation for this. Okay. In other words, knowing these well would enhance your understanding of vectors and usage of vectors, and you can use it for other places. Okay. So I want to start with this. Actually, let me start here. Okay, so this is, I guess, less well known. Who knows what the formula is for?
Torque.
Yeah? Torque, right? That's for torque. And a lot of you probably have seen the formula for the torque without the sign. But when it comes to the version with the sign, does anyone know what sine theta is for? What's sine theta? Or when do you not need the sign? Does anyone know? When is it just torque equals to F times R? Yeah?
When it's 90 degrees.
Yes, exactly. So when you're, let's say here's what do you call this when the point when you try to rotate? I don't know. Let's say you have this point that you're trying to rotate and there's a rod of length R, and if the force is perpendicular to this direction of the R, then the torque that's applied to this point is given by torque equals to F times R, right? But then when you have an angle, so this is when it's 90 degrees, but if you have, so I'll just write here over here, torque is that, okay? But if you have, how many of you are taking statics right now? Oh, most of you, okay. So you do torques a lot, right? Are you already using torques?
Not yet.
Not yet? Okay, yeah. So you'll be using torques very soon, okay? Yeah, so you should definitely know what this is, and then when your vector, the R vector, you should really think of this R as a vector whose magnitude is the length of this rod, and the direction is direction from the point, the pivot point. I guess that's what it's called. Okay, so from the pivot. So this vector is like that, and then if you apply some force F to this, then the angle between the two vectors will be, this will be the angle between the two, right? Because vectors you can move around. So if you move this vector over here, then the angle between the two vectors is this angle theta, right? So that's the angle theta. But if your force is acting not in 90 degrees, but it's like this, then you only the component that's perpendicular to F is really working towards to rotating this rod, okay? So you need this component right here, this component of this force, and note that you're not really finding the component in the direction of R, but rather it's a component that's perpendicular to R. Do you agree? All right. So so this point right here is what is it? Is the component of F in the, not in the R direction, but in the perpendicular direction. That's what it is. Okay? And just by using SOHCAHTOA, I said this several times, but just remember when you have when you're trying to project something, if you're getting this component where the vector and that component has the angle between, that's cosine. So this part is F cosine theta, whereas this side, which is the opposite of the angle, that side is the F sine theta, right? So that's a must for you to know a little later in static, because in statics, they ask you something like the force that's on, say there's like let's say there's a pub and there's a sign. Usually pub has signs like that with some beer on it, something, right? Then they want you to figure out how much force is here, and there's like a string tied here, and there's always this angle between the two, okay? And this angle, you need to multiply sine of this angle to get this torque that's applied to this endpoint, okay? So all of these are really needed. You may only have seen a few questions in physics and at the end of the physics that uses this, but in your statics course, this is going to be used a lot more, right? Okay, so so that's where the first idea of the cross product is that you have a situation where you remember that for the dot product, it was you multiply the magnitude and you multiply the cosine theta, right? And here, the situation is a little bit different. It's you multiply the magnitudes and you multiply the sine theta, right? So that's one thing that you have to know. Let me erase this part. We'll keep this one. Now, another problem is that. Let me ask another question. Is torque a scalar or a vector? Does anyone know? Is torque a scalar or a vector? Yeah?
Vector.
It's a vector. Okay, so vector must have a direction. So suppose you have a rod like this and there's a force like that. Which direction is the torque? See, torque is rotation, right? So how do you assign a direction to something that's rotating?
Right.
Use the right hand rule. That's exactly right. So what you do is you think about the direction that's rotating. You use this right hand, and you assign the perpendicular direction. And that's a convenient way to assign direction to anything that's rotating. Say, if you have any rotation in 3D, there's always a plane of rotation where that thing is rotating fully within that plane, and then you apply the right-hand rule. So that's the assigned direction of this torque. Is that okay? Yeah. So you may have okay. So this is where my engineering knowledge fails. I don't know how this works, but there should be like a case where you have something like a ball bearing, but you have like two different rods where forces are acting differently. So you have like one thing trying to rotate that way, another thing rotating this way. Now, how do you add these two vectors? Well, if you assign the direction exactly like how I described them, like if you're rotating, it's always rotating with respect to one plane, right? And if you assign the vectors with directions as I described, and then you add them, then you see that the sum of those two torques will end up giving you a total torque that's rotating a third plane. If one rotation is this way, another rotation is that way, and if you add the two vectors, then that's going to be yet another plane that's somewhat in between the two. So that's how the torques work, okay? So hopefully you got that. I mean, pretty much all of you need to know this. So hopefully you don't completely ignore this. But since this is really a math course, even if you didn't fully understand, now let's just jump back to math. Uh, See, the nice thing about math is that in math, we just get rid of everything that looks complicated and try to just catch the core idea. That's why math is so powerful. When you just catch the core idea and look at the mathematical structure, surprisingly, the same mathematical structure appears in other places, and you don't have any trouble with it because you already have experience in the previous one. So just to give you an idea here, I think there's something called F equals to, um, no, I shouldn't do that. BIL sine theta. Do you remember this one? What is this for? Yeah.
Magnetic fields.
Yeah, B is magnetic field, I is current, and L is the length of the wire that the current is flowing, right? And you have the sine theta. You've never heard of the build a science guy? You remember this formula is like force is build the science guy. Well, it used to be like that. Now all the physics courses they just give out the formula sheet. I mean, you need to know the formulas in order to really fully understand. I really don't see a point of giving formula sheets. But this is another place that the same thing appears, right? So this IL becomes one vector and B becomes another vector, and the result is a force, which is another vector. Okay. So these are the places where the cross products appear. Let me just delete this one. So fully understanding one operation will allow you to understand the other one. See, this one uses right-hand rule. The build a science guy formula also uses the right-hand rule. Okay. So we say the following definition. Suppose you have U V and the cross products only work in 3 dimensions. Okay, so UV are 3-dimensional vectors. Then W equals to U cross V is a vector with the following prescription or following description. And the descriptions are, well, how do you describe a vector? You just need the direction and magnitude, right? So first, the magnitude is given by exactly what we discussed. It's the norm of U times norm of V times the sine of theta. Okay. And another thing that you should know is that because angle between two vectors can only be between 0 degrees to 180 degrees, right? If you go beyond 180 degrees, it becomes smaller again, okay? And in that domain, sine is always positive. So that just makes sense, okay? And then the direction of W is given by the right-hand rule. Okay, so that's the definition of a cross product. Okay. Now, this definition is not so easy to digest But just like the dot product, the cross product will again come with some nice formula. It's more complicated than the dot product, but it's doable. At some point, you will be given a formula. But here's already one formula that you should always remind yourself. Okay, the norm of the cross product, and the norm of the cross product is given by the norms multiplied times the sine base. So let's try to work with the first example. Suppose u is equal to, say, 1 comma 0 comma 1. No, 1 comma 0 comma 0. And v is equal to 1 comma 1 comma 0. Compute u cross v and v cross u. Okay. To do this, let's first figure out what this picture means. So let's say this is z, that's x, that's y. One comma 0 comma 0 means starting from the origin, you go one step to the x direction, but you don't take any more steps on the x or y. So this vector will be your u vector. 1 comma 0 means you step 1 in the x direction, and then you also step 1 in the y direction. So this point here at 1 comma 0, this is the point 1 comma 0. You take 0 steps in the z direction, so this is still at the ground level. So imagine that xy plane is the ground level. So if this is x, that's y, and that's z, then u is just one step here, and v would be there. Okay, so you have these two vectors. Is that okay? Yeah. So that's the vector we have. That's the vector. Okay, first question, what's the angle between the two vectors? Yeah? 45 degrees, right? Yeah, you should have that intuition. Because this is like exactly in the middle of these two. And this is 90 degrees, so it's half of 90 degrees, it's 45 degrees. Therefore, when you say W, so let W be U cross V, then the norm of W would be norm of U times norm of V times sine of 45 degrees. Well, this is obviously size 1 because you only took one step, times size of V would be, again, the sum of squares and square root, right? So 1 squared plus 1 squared plus 0. And sine 45 is square root of 2 over 2, right? And that gives you, oh, it's just 1. Okay, so it's some unit vector. That's because this is square root of 2. Square root of 2 times square root of 2 is 2. 2 over 2 is 1. Okay, so you get a 1. Now we have to figure out the, let me, sorry, I should have written something here. W is given by the perpendicular direction. Chosen by right hand rule. So, see, as I said, when you define torque, the direction of the torque is always, we just conveniently choose the perpendicular direction, but we choose the direction by the right hand rule. Okay? So, what is the direction that's perpendicular to these two vectors? So what's the plane that containing both u and v? Yeah?
The z-axis.
Yeah. So the plane that contains u and v is the xy plane, right? What's the perpendicular direction? Is the z direction, right? But see, there are two perpendicular directions. There's one going up, the other going down. Which one is it? Well, we said uv, right? So since u is, see, this is x, that's y, that's z, okay? Since u is this way and v is that way, when you do u cross v, so you first go in the first vector's direction, and then you wrap your fingers towards the second vector, okay? And that says the direction should be up. Is that okay? Yeah. So the result is that it's a direction that's taking the direction up. And so what is this vector if you go up one in the z direction? What is that? W is therefore?
0, 0, 1.
Yeah, 0, 0, 1. That's it. What if you had, for v cross u, what would change if you did v cross u instead of u cross v? Yeah?
V would be in the right hand.
Right, so when you apply the right-hand rule, it's different. Remember, u is this direction and v is that direction, right? So this time, you first have to put your hand in the v direction, but then when you try to wrap your fingers towards the u direction, which is over here, you can't do this. You have to flip your hands this way and then wrap, and therefore, where's your thumb pointing to? Downwards, right? So this is, you see that v cross u is exactly negative of u cross v, which is negative of 0, 0, 1, which is 0, 0, negative 1. Okay? And this actually would happen all the time. So note, for any two vectors, it's always true that u cross v and v cross u are direct opposites of each other. Because if you look at the formula for the magnitude, that doesn't change. Whether you have uv or vu, that doesn't change, right? But the direction changes. You have the same magnitude, but opposite direction. So that's always true. Okay? So that's how you would use this definition. It's a formidable definition because you have to carefully figure out their lengths, figure out their angles, and then only when you get those angles, you can figure out whether you have direction going up or down or some other, it could be something totally different. If I had like vector v as 1, 1, 1, now I'm at a loss. I don't know what to do because you have, so here's u, here's v, but instead of here, you have 1, 1, 1, which is here, right? Then the plane that's containing here is like that, so where's the perpendicular direction? Well, there's a way to figure that out. We're going to learn it later. But at this point, that'll be suddenly very hard to do, right? Okay. All right, so that's what you have. I mean, if physicists were using this torque or other formulas and if that cross product thingy didn't have these extra properties, then mathematicians would have been less interested, and it wouldn't even be like a separate section on multivariable calculus. But it has nice mathematical properties and it makes things convenient. And after all, why is math useful? Well, I already said that math allows you to take out the irrelevant parts and only find the relevant things to better understand one phenomena. And if you see it in other places, you can use the same knowledge as before. But another reason why math is powerful is because if you look at the properties, they become shortcuts. Like here, we didn't have to calculate v cross u all the way from the beginning. All you had to figure out was that this is true. And once you know that, then we didn't have to have a new calculation, right? So math is powerful because it provides you with lots of shortcuts. And why do shortcuts work? Because it satisfies nice mathematical properties. So whenever you see some mathematical property, you want to take a mental note of it because you can use them later in some other context for your own good, for shortcuts, okay? So the first one is what I just said. So u cross v is equal to negative v cross u. And if this didn't have a minus, then we would call this as commutative. But since it has a negative, we call it anti-commutative. Now, another thing is that, interestingly, because u cross v is a vector, you can multiply another vector to it. So you can have a triple or any number of multiplication you want. You couldn't do that. You can't do u dot v dot w. This doesn't make sense because this is already a scalar, and you don't have a dot product between a scalar and a vector, right? So that doesn't make sense. But here you can do that, and this is same as u cross v cross w. And what is that? That's called associativity. And probably the most important property is that if you have u cross v plus w, this is same as u cross v plus u cross w. Okay, well, what is this called? What's the name of this property?
Distributive property.
Distributive property. Okay. And then there are a few others. So for example, if you have u cross u, that's going to give you 0. And by the way, this is a 0 as a vector, meaning that it's really 0, 0, 0, okay? And the reason is, if you have one vector, another vector, what's the angle between them?
0.
0. And what's sine of 0? Sine of 0 is 0. Cosine of 0 is 1. Sine of 0 is 0. You should always remember this picture. This is a sine graph. This is a cosine graph, okay? You can see that sine is 0 at 0. Cosine is 1 at 0, okay? Yeah. So make sure, whenever I ask you this question, what is sine 0? Immediately, you should think of this picture, okay? Don't remember the values because it's not going to stay with you. But pictures, they stay with you a lot longer, okay? So sine 0 is 0, cosine 0 is 1. You get to use this a lot again in other classes, so you should probably memorize this, okay? And since this is 90 degrees, it's 90 degrees, you see the sine of 90 degrees is 1 and cosine 90 degrees is 0, okay? And this was why when you have a dot product between two vectors that are perpendicular, you get 0. That's what we were talking about last time, right? Okay. But for cross products, because sine 0 is 0, you get a 0 when you have the same vector. So don't write this down, but I just want to remind you that if you had a dot product of any vector with itself, what do you get? This is the norm squared, right? That's because cosine 0 is 1. Okay. So that's another one. Am I missing anything? Oh. This is an important property. Norm of U cross V is the area of the parallelogram formed by U and V. This is almost by definition. If you have length U and length V, and you can form a parallelogram to it, right? So one thing that you should know is that this triangle that has one side as V and other side as U has the area equals to 1/2 UV sine theta. Have you seen this formula before? 1/2 AB sine theta for the area of a triangle with angle theta in between. Okay. If you haven't, you should know this. This is a very important formula. Okay. So area is 1/2 A times B times sine theta. That's a very famous formula for area of a triangle. Yes.
So with the area of the parallelogram, it should it is the same as the norms.
Yeah. So now the parallelogram would be double of this, right? So that's why this is what I mean. This is norm of U times norm of V times sine theta, right? So that's exactly according to this formula. It's the area of the parallelogram. Okay. So often, what you're going to learn is that if you're given two vectors and you're asked for the area in between, you're going to calculate their cross product. If you want to get the area of the triangle, you're going to calculate the cross product and take the norm of that and take half of it to get the area of the triangle. Okay, so that's going to come later in the exercises. If we have time to do some exercises, that's what we do. And number 6, U cross V is perpendicular to both U and V. Okay? Which has the following idea. So, i.e., if you have U cross V and do a dot product with U, you get 0. Because if you have two perpendicular vectors, their dot product is 0, right? And then U cross V, do a dot product with V, that's again 0. Okay? But all of these properties would be useless if we didn't have a nice simple formula for the cross product. So now I'm going to do some calculations leading up to the formula. It will be very helpful to see how it's derived because then you'll have some comfort when you use them. So try to follow my reasoning as much as possible. So first of all, we talked about the I, J, K unit vectors, right? What are these vectors in 3D? I is one step in the x direction, right? J is one step in the y direction, right? And K is one step in the z direction, okay? So those are called standard unit vectors. So I is 1, 0, 0, J is 0, 1, 0, K is 0, 0, 1. Okay? Now what I want you to think about is what's I cross I?
0.
0, because we just said that, right? Anything with the self is okay. What's I cross J? Okay, so I is this way, J is that way. What's the area of the parallelogram? Well, in this case, it will be just a square, right? With this length 1, this length 1. What's the area? 1, right? Where's the direction? Up, right? The right-hand rule goes up. What's that? What's the vector that's one step going up? What do we call that? K. Okay, what's J cross I? Negative K, right? We just learned that it's anti-commutative, right? Okay. How about I cross K? Oh, that's harder. I cross K. So I and K. Okay. So which direction is that? Is it?
Negative J.
Negative J, right? Because you go this way and then you have to. So I and then J direction is, no, K direction is here, right? So if you do the right-hand rule, it's going that way. So it's negative of J. Yeah. Oh, by the way, when we talk about the coordinate system, if you do X, Y, and Z, that's called the right-handed coordinate system, okay? If you do X, Y, and then Z, that's the mirror image of what I just described. That's called the left-handed coordinate system. That's we don't use that, okay? Whenever we talk about dimension 3 and impose a 3 axis X, Y, Z, we always use that X and Y, and then use the right-hand rule to determine where is the Z axis, okay? This is the positive Z axis, okay? All right, so when we do this calculation, we're always doing the right-hand rule in the right-handed coordinate system, okay? So I have I cross J as negative J. That means K cross I is
Positive J.
positive J. Good, yeah. And then what about J cross K? J is here, K is there. So you do this way, and then you have to turn your fingers up. So that must be this way, right? So where's my thumb pointing to? It must be I, right? Okay, and then K cross J must be negative I, right? Okay, so those are some building blocks. And I said this number 3 is the most important. It's because this rule, well, you can first prove this geometrically, just like how I showed you how to prove the distributive property for the dot product. If you had the dot product instead of the cross product, you also have distributive property, okay? This one you can also prove by drawing some pictures, but it's 3-dimensional, so it's really hard to decipher. So even if I try to explain it to you, it'll be very hard to understand. But let's just suppose that this is true. And as I said, we're trying to come up with the formula, right? So in order to get a formula, we're going to assume that you have two vectors, A1, A2, A3 as the first vector, and B1, B2, B3 as the second vector. Okay? Now let's see how we can make use of everything that we found. And the way we do it is by saying, well, that's same thing as A1 times 1, 0, 0 plus A2 times 0, 1, 0 plus A3 times 0, 0, 1 cross B1, 1, 0, 0 plus B2 times 0, 1, 0 plus B3 times 0, 0, 1. Right? Because if you multiply this inside, this will become A1, 0, 0, 0, A2, 0, 0, 0, A3, and then if you combine all of them, you end up with A1 plus A1, A2, A3, right? So it's just a like long way of writing things. But the reason I want to do this is because now I can write it as this vector is what we call as I. A2 times the next vector is J, A3K, right? You do cross product B1I plus B2K, no, J, and then B3K. Okay. And then we expand, right? We just FOIL. Okay. You usually FOIL it for like two terms times two terms. You have 3 terms and 3 terms, so you really need to try to pair everything that you see. So you will see A1I times B1I, and then this, and this, 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 this. So it's just trying to come up with all the pairs, and then you write down the result. Okay, so let's do one by one. So first question. What's A1I times B1I? That's going to be A1 times B1 times I cross I. What's I cross I? 0. So that's 0. Okay. Now when A1I gets multiplied to B2J, what do you get? Well, that's A1 B2, and you have I times J, right? What's I cross J? K, right? Yeah, I have the results there. Okay. By the way, these are just temporary results to get the final formula. I'm going to repackage the final formula in a nice way so that you don't have to worry about that, okay? And then I, what's next? I cross K, right? What's that? Negative J. So it's negative A1 times B3J. Okay, so just to make sure that you guys are understanding what's going on, try to write down what you get if you do A2J cross B1I. Think about it. What would you get? Okay, what do you get? A2J, B1I. So what do I write? Negative A2, B1, K. Get it? Okay, and JJ, what do you get? 0. Anytime you have the same direction, the angle between them is 0, sine 0, so you get 0. Anytime you have 2 vectors in the same direction, it's 0, okay? And then JK. What does this give you? Here. JKI. So it's going to be plus A2B3I. Okay. Then KI. KI I have it here. It's positive J, so it's plus A3B2J, no, B1J. Then KJ. KJ would be negative I, so it will be negative A3B2I. And then the last thing is 0. So zeros I don't need to write. Okay? So I have a total of 6 terms. But you see that some of them have the same vector, so let's combine them again, and this is what we can write down. It's A2B3 minus A3B2 I plus, for the J, it's negative A1B3 plus A3B1 J, and then plus, for the K, it's A1B2 minus B2A1 K. So that's the formula for the cross product, okay? But it's just too much, isn't it? Right? How are we going to memorize this? So we need to yet try to repackage this in another format that's easier to calculate. And to do that, you have to use something called determinants. Okay. Now, if you have seen determinants before, that's wonderful. If you haven't, I'll just teach you what it is, but then we'll be doing matrices soon, and we're going to discuss determinants more there. Okay. So this one happens to be equal to the determinant of I, J, K of A1, A2, A3, B1, B2, B3. Okay. It's called the determinant. Now it looks really nice, right? But then if you don't know what a determinant is, it's just a nice formula that you don't know how to calculate. So we still need to learn how to calculate. The way you calculate a determinant is the following. If you have a determinant, well, first of all, determinant of 2 by 2 is it's like a fish shaped, okay? And by fish shaped, I mean it's like AD minus BC. Okay? You do this. That's how you do the determinant of two things. You calculate determinant of ABCD as AD minus BC. That's how you calculate the determinant of 2 by 2. And if you have 3 by 3, that takes some time to calculate because A, B, C, D, E, F, G, H, I. The way you calculate a 3 by 3 determinant is you select one entire row or one entire column. It doesn't matter which one you take. You just take one. For this kind of calculation, it's often easier to just do the first row. So I'll just explain how to do expansion by first row. So let's say we choose the first row. Then what we do is every time we meet an element, write that element down, okay? Times, you cross out the column and the row containing that element, so you get that, right? And you make a smaller matrix out of what's known as the minor matrix. That's called the minor matrix E, F, H, I, okay? And then apply a checkerboard of signs. So there's a checkerboard of signs. Let me just write over here. Checkerboard of signs is you always start with a plus on the top left corner, and then you alternate. Just like that. Okay, so you make a checkerboard out of pluses and minuses. And because this element has plus, you don't modify it. Okay. And now you go to the next element, which is B. So put B. Okay. Cross out the row and the column. What are you left with? D, F, G, I, right? So you have D, F, G, I as the minor matrix. And whenever you have a 2 by 2, remember it's D, I minus G, F, G. Okay? So you can always calculate a 2 by 2. And then you apply the checkerboard of signs, which is minus. Right? So that was confusing because we actually have to go through 3 steps. Okay, the 3 steps are go through a column or row. This is a row. So you go through every element, choose the element. That's first step 1. Step 2 is write down the minor matrix obtained by deleting the row and the column. Okay, and then step 3 is apply the checkerboard of signs. So there are 3 things that you have to remember. Okay, so the last one, what is it? I have the last one as C multiplied by the minor is D, E, G, H. Okay, and then it's a plus because of this checkerboard of signs. Okay, you do this, and that's how you calculate the determinant, right? Okay, so that's the explanation of the formula. And from this point, you only get better understanding by doing more exercises. So let's just do a few more exercises. I'm going to start with example 1. Example 1. Find a vector that is perpendicular to (1, 2, 1) and 2, (-1, 3). Okay. So let's say we have that. Now it's this question is asking for finding any vector. Okay. So of course, if you have two vectors, if you're given any two vectors, there's a line of vectors that's perpendicular because two vectors form a plane, and the perpendicular direction has many, many vectors in it, right? They're all multiples of each other, right? But later, you need to be able to do this. Now, don't write this suggestion. I just want to give you some ideas of how this could be approached in a different way. You can solve this question by doing the following. Just say A, B, C is perpendicular to both. For perpendicular vectors, what do we know? The dot product is? 0. So you set this as 0. And the same vector has to be perpendicular to 2, (-1, 3) as well, right? And they will give you a set of equations, which is A plus 2B plus C has to be 0. And this is 2A minus B plus 3 is 0. 3C is 0. Okay? Now that's an underdetermined system because you have 3 unknowns and just 2 equations. But that's what we expect because there is not a unique vector. There are infinitely many vectors. So you just have to find one solution of this. And the way you could get it is, for example, you can just set C as 1. Just pick one random value, right? And then now you have 2 equations for 2 unknowns A and B, and you solve that. You get some not so pretty numbers. It's like lots of fractions. But that could be one answer, okay? So that's one way to do it. But we have a more convenient way to get a perpendicular vector now. What is it? What do you use? This, right? Cross product. Cross product gives you a perpendicular vector. So yeah, that's a lot better than having to do something that I just described. Okay, so the proper solution is just to take the cross product of 1, 2, 1 and 2, (-1, 3. How do you calculate this? Well, this is going to be, well, let me put it over here. So that's going to be equal to I, J, K, and then 1, 2, 1, 2, (-1, 3. Done. Okay? Oh, it's not done. We still have to calculate what it is. All right, so let's try this. It's I times what? Give me the minor.
2, 1, (-1, 3).
Yeah. So if you take out the column and the row containing I, you get this vector, this matrix. That minor matrix, 2, 1, (-1, 3. Okay? Now the checkerboard of signs is plus, minus, plus. So J has to have a minus. Okay, what's the minor matrix this time?
1, 2, 1, 3.
I'm taking out the J, this column and that row, right? Anything that contains J is illegal. So what's left?
1, 1, 2, 3.
1, 1, 2, 3. Okay, and then checkerboard of signs is positive for I and K and negative for J, okay? And then is 1, 2, 2, (-1. Oh, sorry, I should have mentioned this, I forgot. I wrote down some complicated formula and suddenly jumped ahead and said that's equal to this. That's something that you have to check, okay? So when you expand this using the rules that I explained here, then write down all the terms for I, J, and K, you get exactly the same formula that I calculated over here. So that's why this is, at the end of the day, that's the only thing that you have to remember. Well, at the end of the day, what are the things that you have to remember? Well, you have to remember that this is the formula for the cross product, and that the norm of the cross product is product of the magnitudes times sign. Okay, it's the area of the parallelogram, and the direction is given by the right-hand rule that's perpendicular. Right. So those three facts: direction of the cross product, the norm of the cross product, and this formula. Those three are the only thing that you have to remember after this class is over. All right. I gave you a lot of motivations where it came from, but that's the thing that you have to remember, right? Okay, so let's continue with this. How do you calculate this? 2 times 3 minus -1 times -1, right? So it's 2 times 3 minus 1 times -1, okay, minus j. Here it's like this, so it's 1 times 3 minus 1 times 2, right? This times this minus this times this, plus k. This time it's 1 times -1 minus 2 times 2. 1 times -1 minus 2 times 2. And let's just calculate one by one. You have 6 plus 1, that's 7i. What's that? 3 minus 2, that's 1, but there's a minus, so it's minus j. -1 minus 4, that's -5. Okay. And therefore, let me see. If I write that vector as the same form as this, it will be 7, comma, -1, comma, -5. Okay? So I claim that this vector is perpendicular to both of these vectors. How can you check? Well, you can check by dot products. Do a dot with this one with this one. What's the dot product? It's 1 times 7, 2 times -1, 1 times -5. If you add them up, that's 7 minus 2 minus 5, which is 0. Okay? And do a dot product between these two. What do you get? 2 times 7 is 14. -1 times -1 is +1. So 14 plus 1 is 15. And then 3 times -5 is -15. 15 plus -15, you get 0. Yeah. So just by quickly doing the dot product of this with both of them, you get 0, and you do see that this is perpendicular to both, right? Which is quite neat, right? By just calculating this, we didn't have to go through solving a system and get some crazy fraction numbers. It just worked, okay? So that's one thing. Let me give you a second question. Example 2. If you have A, 1, comma, 2, comma, -1, B as 3, comma, 1, comma, 0, and O is 0, comma, 0, comma, 0. Find the area of triangle ABO. It's a bit hard to imagine, but say if this is X, that's Y, that's Z. A is go 1 step, 2 step, and you go slightly down. So that's your A. This is your A vector. B is 3 steps, 1 step this way, and then that's it. So you have B vector there, point B there, point A there, and then you have the origin O. So you have this triangle in 3-dimensional space. Can you picture it? Now the question is, what's the area? Yeah. Okay, that seems really hard, but we know that that's basically like saying you have OA, which is this vector, and OB, which is this vector. You have 2 vectors. Those 2 vectors is going to create a parallelogram, And half the area of the parallelogram is what we want. That'll be the triangle. So what we do is just say, let U be, if I want OA, OA is like terminal minus initial, so it's A minus O. So you get 1, 2, -1. V would be B minus O, because by V I want OB vector. So V is like OB vector, okay? And it's always terminal minus initial, so it's 3, 1, 0, minus 0, 0, 0. And subtracting 0 doesn't do anything, so that's what you get, okay? So with those two vectors, now what we want to do is to calculate U cross V. Again, this big calculation, right? So you have I, J, K, 1, 2, -1, 3, 1, 0. Now, once you get familiar with this determinant calculation, it's not that hard. You can just do this by mental math. So for I need this minus this, right? So it's 2 times 0 minus -1 times 1, that's positive 1. So you get 1I. So it's not that hard, okay? And then you have minus J. And what is that? If I cross this out, it's 1 times 0 minus -1 times 3. So that's 3 here. And then plus K. And then if I take the row and the column out, it's 1, 2, and 3, 1. So what is that? What's that? 1 times 1 minus 2 times 3. What's that?
-5.
-5, right? So that's going to be 1, -3, -5. That's the cross product. Okay? So if you get used to, although I said there's like 3 steps in calculating the determinant, it sounds really complicated. Once you get used to it, it's not that bad. Okay. Not only that, there's also, if you look online, there are other tricks too. There's another one which says you copy the first 2 columns, like I, J, 1, 2, 3, 1, and then you just do, you only write the diagonals that goes through triples, okay? Yeah, so these don't count, these diagonals don't count. You only go through the diagonals that go through triples, and this is the positive ones, and if you go this way, those 3 are negative ones, so you just multiply through, and you do this minus that. That's another way. Some people, instead of copying it this way, they would copy this down here, and then do that, okay? Yeah. So if you look up, there are several tricks that would shorten the calculation, but at the end of the day, all roads lead to this answer, okay? So that's your vector, but what do we want? We want the area, so what do? We need the magnitude, right? Magnitude is, the magnitude of the cross product gives you the area of the parallelogram, right? So we take this, which gives you 1 plus 9 plus 25, which is square root of 35. And because the triangle is half the area of the parallelogram, the answer would be square root of 35 over 2. That's it. Now imagine having to solve the same problem using other methods. What do you think? It would be horrible. It's very hard. Okay? So although this cross product calculation does seem pretty involved, I mean, it's amazing. It's amazing how you can have such a formula to be able to let you calculate things like this, right? Yeah. You have a question? Yeah.
How'd you get over 2?
Oh, that's because this is the area of a parallelogram. This is the area, but what we want is just the triangle, which is half of the parallelogram. Yeah. Right, that's all for today.